and math.
That one, yeah.
So welcome to the second part of the morning session. We start with Antonio Morais on sculpting the standard model from low-scale gauge Higgs-Matter unification. Grand unification, sorry.
Thank you very much, Werner. And it's a pleasure for me to be finally, after almost 2 years, giving a talk not to a computer screen. And as you may guess, so this is a talk on grand unification. But this is a new idea that I hope you find interesting of low scale. In fact, of low scale unification. But in fact, this is not, we didn't aim at having this low scale unification in the beginning. It just came out as an outcome of the model that I will show you now. So these are my collaborators that work in this. And here we have these two archive references that we very recently posted this, this work. Right, so let me start with the standard model just to revise. So all of us know very well the gauge symmetry that describes the structures of the standard model along this horizontal direction, mostly. Here you have the fermions, here you have the bosons, including the Higgs boson here. And also, we know the space-time symmetry described by this Poincaré symmetry. And also there is a family replication. Typically, it's possible to describe models with family symmetries. There are many experts here as well, and you can explain the family replication from the nature. Also, the part of the gauge symmetry can be fundamentally, or can be embedded in a more fundamental structure in the context of known grand unified theories. So what's happening here? Okay, it wasn't me. If you want me to rush, no worries. Okay, back here. So we can also relate to this fermion side and this bosonic side via supersymmetry, extra dimensions. There are many works out there where these things can be found. However, the idea and the ideal would be to being able to put everything together instead of separately addressing these points, putting everything together in a single structure, like one model that could put all of this together at once. This was our goal in this work. So, but to see that, let's go back to the early 80s and look at the exceptional chain. And the exceptional chain, we can start with the standard model gauge group, the exceptional chain in terms of linking diagrams. And here in the first line, so these are the scalars of the standard model, which is the Higgs. These blue ones are the fermions, the quarks and the leptons, and these purple ones are the gauge bosons. So they are in 4 dimensions. They are vectors. If you go up one level to SU5, which was actually the first gut proposed by George and Glashow back in 1974, you put all the gauge fields in the same unified representation. So this is gauge field unification. But you can aim at more, and SU10 can embed also each family of fermions in the same 16-dimensional representation. It also gives you a right-handed neutrino. But you still have to do that separately, like 3 copies of this 16 plate, and gauge field unification is still there. If you go up to the level of E6, then you see something nice. So the fermions and the scalars, they are embedded in the same type of representation, these 27 plates. They can be like that. And this suggests supersymmetry. In fact, E6 becomes rather elegant if you add supersymmetry. So let's extend our space-time symmetry and add one supersymmetry. And this is like the minimal supersymmetric E6 model, where you still have gauge unification, and separately you also have Higgs and matter unification in 3 copies of 27 plates. But let's aim at more and go up. This is at level of EEST, and this is E7, and this is the first time you have you no longer have here the 3 times. In this rather big and I would say ugly representation, you can embed also the families. But there is a problem here because these are real representations. This is a real group, and it's at least in 4 dimensions, it's problematic to get chiral matter out of it. So this suggests the idea of orbifolding, where with additional dimensions, in this case just as an example of 6 dimensions, so 2 extra dimensions, you can also then say that you have a model with family unification, and by orbifolding you can separate chiral and anti-chiral matter, and having massless chiral matter at low scale. But we can go up one more level to the E8, and at the E8 level you also see something nice. The chiral and the vector fields, they are of the same dimensionality. So this in fact suggests something else, that you may be able to put these 2 together, and that is realizable if you go to 10 dimensions with 1 supersymmetry. And this is what our starting point. This was our motivation, where you can embed everything. So you can have a gauge, matter, Higgs, and family unification in this single 248. So this contains a 10D vector and a 10D chiral / Majorana fermion. Right. So this is the model setup. So it's a 10D quantum field theory, super young Mill theory based on E8. It has a 10D vector and a 10D wild fermion in the joint representation of E8, which is also the fundamental one. But bear in mind, this is not a string theory. We are not doing string theory by any means. It's actually deliberately our intentions not to propose an alternative path. So we don't have gravity here at play. Of course, if you want fundamental gravity, you need to go to string theory or additional degrees of freedom because of anomalies and so on. But this is not what we do. I will say one more word about this in my last slide. So our model has 10 dimensions, so 6 extra dimensions. But this, as it stands here, these dimensions are opened, which is not realistic. So we ought to do something about this super Poincaré symmetry. Also, E8 has not, as it stands here, has no chiral matter yet. So what can be done is adding this lattice and these orbifold groups, which make this symmetry incomplete. And by incomplete, it means, and now you see here, it's a semi-direct product instead of direct as before. It means that not all generators that are here will commute with the 8. And if you make it so that only the standard model generators commute with the 8, you reduce just by choosing this gamma and this F, you will break all generators that are non-standard model and will remain only standard model generators at the end. So basically, you only touch this side, and E8 is simultaneously broken by these geometric means. So this was this was also shown by our colleagues here. So what do we shoot in this particular setup? So we use this z to the power of 6z. I like the integer numbers, z to the power of 6. Lattice, so because we have 6 extra dimensions, and this compactifies the open dimensions into a T6 torus, basically. And as shown here by Ratz and et al., you have this type of generic and abelian orbifolds that preserve one supersymmetry with 2 z's, and you can do this consistently. So what do we choose then for this Zm and Zn? So in this work, we use Z3 cross Z3. That at QFT level, it was not done before. There was Z2 cross Z6 that goes to Patti-Salam and other possibilities. And I recall you that we are doing QFT here, not string theory. So this is just a visualization of this. This would be like a T2, only with 2 dimensions. This would be like a T2, like the Z to the power of 2 lattice, let's say. And to get the orbifold folding, basically what we do is identifying together these dashed lines of the same color, and then all of them together with the purple line. And at the end, you have this. And the fixed points are these blue ones here, where you have a four-dimensional theory. And this can be represented for only one complex extra dimension as this Dorito-like picture with the fixed points here in the edges. Right. So, but this symmetry breaking by orbifolding can be done by choosing Z3s that are part of U1s that are inside E8. And this is an appealing possibility where you have two different Z3s. One of them breaks E8 down to E6 cross SE3 family, and another one to a flipped E6 version where the color group is outside of E6 already. So imagine also that you have some tiny hierarchy or some mild hierarchy between the radii of the extra dimensions. These things can happen almost simultaneously, not exactly simultaneously. And just to see a stepwise possibility. So the first one, let's say the first one is the second line. So it breaks E8, it reduces it to E6 cross SE3 color. Then the second one acts, and you break to the intersection group of these two. So it's the quartification group, like for SU3s, color, left, right, and family. And finally, with the lattice group to compactify the extra dimensions, you have Wilson lines here. So this is associated with translations in space-time. Let's say it imposes certain boundary conditions in the translational group, and you get to reduce the rank and go down to the standard model if you properly align the Wilson lines to preserve the standard model. And you also get rid of any supersymmetry by this, as I will show. So this is quite nice in the sense that essentially there are two major things here. You have one single 248 of E8, which is anomaly free, and at the fixed points you have the standard model gauge group, which is also anomaly free with the standard model content. So to know exactly what are the massless states, you need to look into the orbifold charges, basically the Z3 cross Z3 charges. And those that will be massless are those that are going to be even under this Z3, these two Z3s. And those are the ones that have 1, 1 in each of these columns. So you have here where the gauge fields will be. So you have these ones here. And then this chiral matter, as you see, there is 1, 1 here, 1, 1 here, and 1, 1 here. So there is one of each. And the anti-chiral part is not even in any of them. So this anti-chiral part will be split from this. This will only have heavy Kaluza-Klein modes, while these ones will also have 0 modes. So these guys here are the candidates for the standard model particles, basically the quarks, the leptons, and the Higgs, and also some BSM states. So now we can also choose, because this is part of the freedom that we have in the model, which is not a lot, but we can choose generically to have only a line, so the Wilson lines, which are effective webs, which behave as effective webs, in only one of them, in phi 1. And doing so, with the other two being 0, this always preserves one SU3. And that SU3 is immediately identified with color. In fact, it doesn't matter if it's a phi 1, phi 2, or phi 3. But your labels and your naming should come accordingly to this, to whether you decide to put the Wilson lines or to align your Wilson lines, basically. And with Wilson lines here in phi 1, we have to identify phi 1 with the leptons, and also Higgs are here. And then phi 2 and phi 3 are going to be the right-handed or containing the right-handed and the left-handed quarks. In terms of like electroweak symmetry representations, to be more familiar, you have the L can be decomposed in this way. So this first line is a doublet. These are doublets, so it should be 2 lines here, but this is compressed. And our Wilson lines will generate this effective webs in this neutrino, or because this is a scale, and there is supersymmetry like this neutrino direction and this flavon direction. And the superpotential of this model looks like this, written in terms of standard model representations. And here in the first line, when these Higgs doublets, these green ones are the Higgs doublets, and we have 6 of them, 3 of each. When they acquire VEVs later on, they can also get VEVs via Wilson lines, but here we rely on radiative braking, because if we rely on Wilson lines, because of the hierarchy, that the low scale of I mean, the hierarchy between the Wilson lines and the electric scale is such that it's hard to motivate such a hierarchy in the Wilson lines. So we prefer to generate them radiatively. But once you do so, this gives mass to only second and third generation quark masses because of this anti-symmetry here. And this G is the unified gauge coupling. You only have second and third generation quark masses. U and D quarks are massless at 3 level. And another nice thing happening here is that the Wilson lines induce D-term SUSY braking. So the D-term acquires this structure and it doesn't vanish. And this is it's crucial because this will then propagate into loops. It will induce masses to leptons and up and down quarks, which is a rather nice feature because it will also be associated with a hierarchy in the mass structure of this model. So this is how you generate masses at one loop level for quarks and for leptons. So together with Werner, we have studied something similar in a previous paper that is here in a different context. But these are the type of diagrams where the things are generated. And these D-terms, there are these D-term insertions that communicate the SUSY braking. Otherwise, only SUSY preserving interactions would be allowed here. Here at the lepton side, because of anti-symmetry, you need 2 of them. Otherwise, this would vanish. Because of putting this in one and another side, it comes with a minus sign when you sum 2 contributions and they vanish. So this is nice because for the quarks, the second and third generation, you have the 3-level contribution and some loop contribution. Well, this L is a loop factor and the loop function that we have here in this paper. And for up and down quarks, it's only generated at loop level. For the case of leptons, you have them generated at loop level as well, but with these 2 insertions, there is a little bit more degree of suppression coming from this lambda to the power of 4, the scale that is running here. And for neutrinos, there is also a seesaw that brings you a further suppression. But the nice thing here is that the quarks are hierarchical, which can explain small mixing that we find, for example, in CKM matrix. And for the case of leptons, they are less hierarchical. There are still hierarchies because we have some freedom in the radius, the extra dimensions, and the Wilson line parameters. That's the freedom of our model, also the gauge coupling. And they are less hierarchical, so the mixing is, in principle, larger. So far so good, and without specifying parameters, we seem to have a conceptually viable standard model. For the case of the running of gauge coupling, which is the main point that I want, in fact, to show, we have Kaluza-Klein modes, so the running must be modified. And when they contribute, the running is not logarithmic, but has a power law contribution that dominates it. And what happens is something like this. So you have the normal logarithmic running, then at some point you have some extra, some new physics beyond TeV level, at least. You have some new physics states kicking in, and then still in the 4 dimensions, you have Kaluza-Klein modes contributing, which change the running for something power law. And then things start to merge, or aiming to merge. But then you also have another compactification. So here you start having extra dimensions, 6 and then 10 is here, it's only beyond here. And the running is further modified. And it happens that there are several points that meet always more or less in a short region here. And you can have this meeting, then you have the running, the 6-dimensional running at this stage here. And when you get to the compactification scale, you go to a super Yang-Mills theory, which has 0 beta functions. So it will run constantly all the way up. But the important thing here is to say that here we achieve this unification. This is what we define as the compactification and gut scale, which, as you can see here, is several orders of magnitude, like 10 orders of magnitude more or less below the conventional gut scale. And lambda 3 is the SUSY, so the SUSY breaking scale. So this is where the Wilson lines break SUSY. But now you may be wondering, what about proton decay? And that's the main point. Thank you very much. So for proton, this is the operator that can generate proton decay. And because of the family symmetry, this changes between generation, because of this IK FL indices. So the main decay channel is going to be 2 counts, not 2 pions, but 2 counts. Via mixing, you can also have decay to pions, of course, but it's suppressed compared to this. So this is the main decay channel to take into account. And the point here is that this is the leading order contribution, with a lot of KK modes here running, going inside, and 2 loops. But it's not only the 2 loops that give the strongest suppression. The strongest suppression is coming from the size of the gauge coupling here. And each, so you see, this is, in fact, is like 10 to the minus 2. And each vertex has contributed as 1 power of contribution to this gauge coupling. So when you calculate the decay width, you have this G to the power of 18, and also some loop suppression, L to the 4 because of those 2 loops. And you also have so the gauge, so the unification scale to the power of 8 suppression, but this is not large. So this part alone would not make it to proton decay. What really makes it is like this factor here, G to the power 18 and L4. And then you can make a code and ask, look for all possibilities, allow for the SUSY breaking and gut scale to be whatever you like, all the way up to the conventional 10 to the 17 GeV or so. And now look for all possibilities that have this merging here. If these things start going in the opposite directions, they will no longer merge, so those are not consistent or are not good candidates for a gut theory. And when you do so, these are the only allowed solutions. So this model only allows for grand unification at this level with the gut scale between 10 to the 6 and 10 to the 9 approximately GeV. And also the gauge coupling, you see the value is pretty much 1, is 0.1, between 0.1 and 0.2. And proton, the proton lifetime is here. This is an estimate with that diagram, and this happens at E8 level. I need to mention that this happens at E8 level, as I have shown you, because when E8 is broken, it goes either via this flipped embedding of E6, where SU3 color is already outside of E6, not inside, and or you go immediately to this quartification group, so you don't have baryon-violating interactions there. So the model seems to be consistent with low-scale grand unification and the PeV scale supersymmetry. And this is nice because it's within reach of near future experiments, and it can be either confirmed or ruled out, not in the very, very far future. And what about the Higgs? This is just to finalize. Since this was a very complicated, I'd say, analysis to do, we just had a proof of concept simplification, only considering the 2 lowest, lightest Higgs doublets, one of the up type, another one of the down type. And you see the KK modes contribution here. That contribution is crucial because it makes the up type Higgs want to run quicker down. And then, of course, you have this radiative breaking, as you have in the MSSM happening. And so there are plenty of solutions like this. And because of the KK modes, this has an impact on what are the allowed values of this the doublet's mass here, the doublet's mass at the I scale, which are associated to the Wilson lines. And this is also nice because with this splitting, all the other scalars are going to be at this level here. And in principle, what we have is a conceptually valid model in terms of efficiencies, as our colleagues here Gustavo and Guy worked before in this paper here, if the third lightest Higgs boson, either of the up type or down type, is beyond 150 TeV, so your efficiencies are you are safe from efficiencies. But there is also a further constraint, like the radiative stability of the Higgs mass may point towards. Let me go. Oh, sorry. Let me go back here. In principle, for radiative stability, you may prefer this lower region here, and of course, then you need to confront this with the neutrino masses, with the lepton masses, with also with the BSM states that are here that I don't have time to talk about. But this is the game that you need to play. And finally, of course, in the future, if you want to do a model of unification, we need also to think about gravity. But as I told you, this is not a string theory, so this is not compatible with a fundamental theory of gravity. Okay, I'm about to finish this. So if you want to include gravity at fundamental level, we need to introduce new degrees of freedom, which will of course complicate the picture, or even go to string theory. But that was extensively studied in the heterotic string, E8 cross E8, and so on. But this is not our goal. Our goal is an alternative approach, and it can be realizable in terms of emergent gravity. And one of our colleagues indeed has this paper where he proposed the way of getting this emergent gravity very recently at 4D level, only with the degrees of freedom of a given model. So this is pretty much what I wanted to say. Let me conclude with the picture that we have scoped, or at least found the lines to scope the standard model from a E8 block, and emergent from here we have a low-scale unification picture, which, to the best of our knowledge, is like the first complete theory that has this feature embedded with stable proton decay. So thank you very much for your attention.
Thank you for this nice talk. Are there questions, comments? Yes.
I want to comment on some observations that you made. Could you put the transparency 31?
31. Yes.
Okay. Yeah. You see, you put the hierarchical quarks implying small mixing. That is true in specific realization, but strictly speaking, it is not true. Now, let me give you an example. One can prove rigorously, but it's a very simple proof, that in the limit where only top quark and bottom quark have masses, mixing has still meaning at that time, and it is large. We don't, that's something that has not been solved in the standard model. You know why BTB is, you know, the particle data, you read, you see BTB is equal from unitarity 0.99999.
Yes.
The standard model doesn't say that. What the standard model says that this is an arbitrary number.
Yes,
you know,
true,
it's not calculable, you know. Okay.
Yes, yes.
I just want to do that.
Sure, thank you, Krzysztof.
Please, there's another question over there. No, please.
What's the clarification? I did not got this from the beginning. At the beginning, you had a super young Mills n equal 1, and then you are extending it to
This
extra dimensions. You put n equal 4 because you have to go from n equal 4 to n equal 1, and this is not a trivial task.
Yeah, well, this is
the running, similar kind of runnings, low or low runnings have been discussed before in the literature.
So the point here, thank you very much for your comment, because I didn't mention that this is what we have in fact is n equal 1 SUSY in 10 dimension, but the degrees of freedom match those of n equal 4 SUSY in 4D. If you exactly, it's just like an equivalence, because you can think in terms of n equal 4 SUSY, because when you go to this exactly, because when you go to this to choose the orbifold and so on, you know that with two of them you preserve 1 SUSY. If you have 3 of them, you completely remove SUSY. If you only have 1 of them, you have n equal to SUSY. But to understand that, you need to think of the 10 dimensions in terms of like 4D n equal 4 SUSY to understand this. It was only because of that.
Do you mean that you also that you have this equivalence just for the field content, or also for the running? I mean, when you have the n equal 1 10-dimensional one, do you have a vanishing coupling? I suppose you have one coupling at that.
Yes,
scale.
yes.
So it is vanishing.
It is.
Okay. And
the running is vanishing, is what I mean. The running is flat, is what I mean, right? Yeah, exactly. Yes. The beta function is vanishes. Yes, yes.
Yeah. And when you break when you compactify everything, and this matches the SUSY scale as well, I guess.
Yes.
It all happens at the same level,
yeah.
Which is at 10 to the 6 or 10 to the 9.
10 to the 7, 10 to the 6. Yes, yes.
Okay. Then you have the unification of the 3 gauge couplings by the help of the power law of the KK modes.
Yes.
Okay.
Exactly. That's I should have put while we were speaking.
Yeah, I thought so, but just want to
but that's exactly it. So the 3 go here, they almost unify, but then you have the KK modes contributing, and
so in fact they unify just before this scale, and they run together.
Yes, here they run together, but not 0. 0 is here after the when you go to this 10D or n equal 4 SUSY. Yes.
Yeah, but the beta function is 0, not also the.
Yes, here the beta function is 0.
Yeah. Okay. Let's thank. Let's thank the speaker again and continue. The next talk will be by Tania Robens on constraining standard scalar sectors at current and future colliders.
So many things. everything. You know. Can you hear me? Does it work? Is it good? The microphone? Hello. Ah. Yeah, but I have to hold it. Okay. Now? No. The perfect picture of me screwing up with the microphone. Okay. That, maybe. Okay. But can you still hear me? Is it good? German has also vanished. Okay. We just go. I can start. Okay, very good. Okay, so I have to thank the organizer. Is it good or is it too much feedback? Okay, I stay away. I come to you. Okay, so I want to now check. Here. Where should I go? That's also bad. Okay. We need to exercise next time. Okay, I will try. So I want to thank the organizers, they are somewhere, for inviting me after hearing so many good things about this meeting. Finally, I can be here, and so far it has been very nice. So as Werner said, I will talk about constraining extended scalar sectors at current and future colliders, and this is based on work with a large number of collaborators, which are listed here, some of them in the audience. So there are some introductory slides. I think I can go very quickly because most of these things have already been said in earlier talks today. So usually one says after the Higgs discovery in 2012, the last building block of the standard model has been discovered. What are the remaining questions? One can ask, why is the standard model the way it is? So search for underlying principles or symmetries. find explanations for observations which are not described by the standard model. A prime example is dark matter, or one can try to explain the flavor structure. Or you can take an ad hoc approach and say I want to test which other models will comply with current experimental and theoretical precision and constraints. Okay. The collider landscape, I think I can also go very quickly over this because I think you're all aware of these various options. So currently we have the LHC running as a future option, which has been already approved, is the high Lumi LHC. I right now 14 TeV. I hope this will happen. High luminosity, and then a future possible option is FCCHH. This is under discussion. Then we are at the plus minus colliders. We already heard a lot about this in one of the previous talks. Again, there are various options on the market, supposed to be high priority in Europe with various center of mass energies which are discussed. And a recent revival, I think, have been mu plus mu minus colliders, which are currently hotly discussed in various forums, and we will see what comes out of this later on. Okay, what is the special role of the scalar sector? I mean, again, I think, more or less go through this because you all know it. So this is the Higgs potential in the standard model. The web basically causes masses for the Higgs boson, gauge boson couplings. Everything is determined in terms of gauge couplings V and lambda. And what is important here, I think, is that the form of the potential determines the minimum and the electroweak vacuum structure. Yeah. So, and this has important consequences, for example, for the stability of the universe, electroweak phase transition, and so on. So when one says we already know everything and we have seen everything in the standard model, it's not completely correct, because what we did not check yet are these couplings in the standard model. So triple Higgs and quartic Higgs couplings, they are predicted to have a specific value from the standard model alone, but we have not measured them yet. Yeah, we have constraints on this and projections of possible reaches for future colliders, but so far we don't know. So in a sense, we are not done, even with the standard model test, I would say. So then if you say, okay, let's go away from the standard model, what can I do now, concentrating on the scalar sector? In principle, you can do what you want. Of course, you have to have some sanity checks. So the first sanity check would be to have a suitable electroweak braking mechanism, including a Higgs candidate at 125 TeV that complies with current measurements. And also your additional scalars should not be excluded by current searches and precision observables. Now, nice add-ons could be, for example, that you can push the vacuum breakdown, which you have at a relatively low scale in the standard model to higher scales. I mean, this is the kind of, has been at least the kind of prominent feature of various models, or explain additional features like dark matter or hierarchies in the quark mass sector. Now, of course, there's a multitude of models out there, and if you're concentrating again on the scalar sector, what you can do is add as many as you want, gauge singlets, doublets, triplets, and so on, and this leads to new scalar states. So here's an example of the scalar sector for 2 Higgs doublet models. Okay, now for the constraints, I mentioned this briefly. You can go into more detail. So from the theory side, you need to have a minimization of the vacuum. So the Z-pole equations have to be solved, vacuum stability, positivity, perturbative unitarity, and perturbativity of the couplings. And then again, from the experimental side, what you want is have a viable candidate at 125 GeV. This concerns many measurements which we have now, so for sure the coupling strength, the width, and so on, and agree with null results from additional searches and electroweak gauge boson measurements, especially the width, which have been extremely nicely measured at lab already. Agree with electroweak precision tests. Typically, this is done via oblique parameters, and if you have a dark matter candidate, agree with astrophysical observations if it's feasible. So, as I said, there are many models around. I mean, I have now, in the next remainder of my talk, I will present some results for models I've been working on. Of course, this is just a kind of personal preference, so shouldn't say anything about which model could be realized in nature in the end, right? And I'm also using a large number of public tools. So I just mentioned this here, Higgs-bound 6 signals for comparison with current constraints. Then this 2 Higgs doublet model calculator gives you a nice a variety of variables, which you can then compare to experimental observations and micrometers for dark matter. And there's a long list, so I will mention additional tools on the respective slides. Okay, the very, very simplest model, just as a kind of warm-up, is you have a singlet, a gauge singlet, real singlet, which you add the C2 symmetry. This means you have one scalar particle. This is the potential. This is the standard model like equivalent, and the three additional terms are add-ons in this model. You have new parameters, so the mass of the second scalar, then a mixing angle, which would be 0 in the standard model, and the ratio of the wefts. So we assume this singlet to have a vacuum expectation value. Now on the left-hand side, you see a relatively updated plot now on the comparison of various bounds as a function of the mass of the second scalar between 200 GeV and 1 TeV. This is the sine alpha. So again, remember sine alpha equals 0 would be the standard model, and I compare various lines here. So for example, the pink line is the signal strength measurement. The green line are direct searches for heavy resonances. Then you have constraints from the W boson mass, and as an example, I also show perturbativity of λ1 coupling. And the way to read it is you go to your favorite mass, and then you go up into the first line you meet is the strongest constraint. And what is interesting here is that now, in fact, we already have strong constraints in large parts of parameter space now from direct searches. But then at some point, the W boson mass takes over. So I think this is an interesting thing. And one should remember electric precision is important as well, right? On the right-hand side, you see predictions for heavy resonance going to two standard model-like particles, so di-Higgs searches within this model. Yeah, you see a projection. I mean, this has not been updated, so this was the Atlas combination of early run-to data, I think, but we haven't updated this yet to full results. And you see that in large regions of parameter space, due to current constraints, the model basically does not reach yet the limit. However, for lower masses, you also have constraints already from this within this model. Okay, I go to the next model. Now I add a second doublet instead of the singlet. You have you have 4 new scalars, which I was already showing in an earlier slide. Can you apply a C2 symmetry? In this scenario, this is not broken. So you have dark matter candidates. All of these particles could in principle be dark matter. I choose one, the age, just by convention. Then you have as 3 parameters the masses of these additional particles and some couplings which appear in the potential. And the signatures for this would be electroweak gauge bosons and missing ET or missing energy, depending on your collider. And so far, this has not been analyzed by LHC. Yeah, so I want to emphasize this again and again. This is a very well-known model, has been explored in great detail in theory, but so far no experimental dedicated search exists for this model at the LHC. So here I show you just an example of the remaining parameter space. So this is the mass difference of the charged and the charged mass and the dark matter candidate, and here the neutral mass and the dark matter candidate. So you see that there's a relatively narrow stripe. Yeah, you can also see, because the decays are 2 electroweak gauge bosons, kind of on-shell, off-shell regions for the decay product. And the red points are just some benchmark points which we devised in earlier work, and I will show results for them. I mean, what is interesting again is always this discussion: what happens if I can have the Higgs going to 2 dark matter candidates? So this is the plot now here as a function of the dark matter mass and this lambda 345 coupling, which is important for dark matter. And you see that you're already in a relatively small range, yeah, between minus 0.1 and 0.1. And then if you're below this threshold, the contour, I didn't show it here, but this comes from signal strength measurements. So basically you're constrained already in a relatively narrow region. And then on the other hand, you see this black stuff here. So this is from relic density. So this is an interesting feature in this model, because you have an interplay of signal strength measurement and relic density calculations, which kind of gives you a lowest mass scale for the dark matter mass. Yeah, so I think this is quite interesting. And then the other colors here are red is allowed. Golden points would give you exact relic density, and the brown stuff is direct detection forbidden. As I said, you have the C2 symmetry, so you can only pair produce the dark scalars. So you would have PP going to these final states here, HA, HH plus, AH plus, H plus H minus, at T plus E minus, you have HA or H plus H minus. Decays, as I said, here A goes to the H to 100%. This is dominant. The other option would be to have an A here, which leads to further cascade decay. Sorry. So then what we did in recent work is we tried to compare somehow collider reach. I mean, this is really very preliminary, I would say, because we didn't do detailed analysis for most of these colliders. So we look at the production cross sections for these benchmark points we devised at 13, 27, 100 TeV for PP, at the 10 and 30 TeV for mu mu. And then we devised a simple counting criterion saying what do we need, or what is the kind of cutoff for the cross section to have 1000 events with the official design luminosity of the machine, and we compare the mass reach. The processes basically are mainly determined, the production process is mainly determined really from electroweak processes, so also electroweak couplings, no new physics parameters enter apart from this AA. AA is the final state, which is kind of different because it's mediated via this coupling. So now you see things get a bit more complicated. You have this lambda 345 and in addition mass differences. And especially this is strongly constrained from direct detection and this from electric precision observables. Then you can also include VBF type topologies, which would lead to additional jets or neutrinos depending on the collider. And this in fact starts being important. Okay, so I show you the sensitivities in figures. Again, the lines are the cross sections you would need for 1000 events for the design luminosity. On the left, upper left, you see here as a function of the mass sum of the produced particles, the cross section in femtobarn, two different lines for now and Tailumi LHC for various production processes here. And you see that basically all of them follow this pattern of a decay as the mass sum increases, which is due to only phase space being the important parameter here. Apart from this AA, there are slight differences because the couplings are different depending on the process. But apart from this AA, where really things are jumping up and down, and this is due to the fact that this depends really on this kind of slightly different coupling here. Okay, and you can see already you can read off at Tailumi LHC, we would go in principle up to 1000 TeV as a mass sum with this counting criterion. On the right hand side, we do the same plot for various center of mass energies, now only for selected processes, 13 TeV, 27 and 100. And you can again see that, especially for the 100 TeV collider, I mean, this would be, in a sense, everything, or at least 1000 events would be produced. Again, this is without the detailed discussion. Yeah. Now then, on the lower left, we say what happens if we include the VBF type signature here. Things are getting more complicated because many more diagrams contribute. It's now only not this S-channel trillion production, but you have a lot of different diagrams. And this leads to kind of interesting structures involving interferences and cancellations, which are not so easy to understand. Okay, thank you. Which are not so easy to understand, but you see, especially for this AA, which was kind of hopeless here, and we didn't even plot it here anymore. Now things are getting more interesting, and the reach really gets expanded, including this VBF type structures. And on the right-hand side, we played the same game for muon colliders. Yeah, and again, the structure here is not so clear, so you don't have this pure falling behavior. But on the other hand, it's possible at 30 TeV, you're really basically covering nearly the whole mass range we were looking at. So this is the same in numbers. Again, high energy, I mean, after Tailumi LHC, basically you reach the sum of masses up to 1 TeV, apart from the AA channel, which is much lower. And then you can go through your different collider options, and all others means now all channels apart from this AA channel, which is special. You're basically there with all other options apart from this AA. And then if you use AA only, maybe at the PP colliders, things work out nicely, especially at FCCHH. And if you include VBF type topologies, then you're doing even better. I have to say here for clicks, I added the numbers, but this was done on a very different level. So this is based on extremely detailed investigations, including everything, background signal, Beamstrahlung, and so on and so forth. So in a sense, I mean, I put it in the same table, but they have been derived on a very different level. Yeah. Okay, so I jumped. I had 10 more minutes. Now I have 8 more minutes, maybe. I jump to the next model where you add 2 real singlets, and I'm concentrating on the case where all scalar fields mix. So now you have 3 scalars. This is, of course, interesting. One can give a 1-hour talk on this model. I don't have 1 hour, so I concentrate on something particular. This production process, so you have a heavy resonance going to a second resonance above 125, and H1 is the 125 GeV resonance going to 3 standard model-like scalars, and then to 6 beats. And this was a benchmark plane we suggested in an earlier work with Tim and Jonas. And then we did a detailed analysis here with Andreas and Gilberto, looking at whether this is accessible at high Lumi LHC with a long chain of tools. These are the production cross-sections here for this triple 125 final state. Here, going up to, let's say, 50, 60 femtobarn. Maybe you cannot read it so well here. I apologize, but what is important is that you really see as soon as this M2 is above 250, you have large cross-sections, and below it's basically impossible. We did some detailed analysis. I don't bother you with this. What is interesting then, in the end, we selected some benchmark points, and basically already with the current integrated luminosity, one could, in principle, if one combines the 2 results, already reach up to 5 sigma for certain of these benchmarks. And then if you go to high Lumi LHC, I mean, they should be all visible. So this is important. I mean, it's the triple Higgs signature is a way to probe the quartic coupling, but also in BSM models, I think it's the first good way to check how one can even look at such a final state with 6 beats. Yeah. Okay. Other channels are also there, of course. So heavy scalar production to ZZ and W, and they are also supposed to cover basically the whole region, including our benchmarks. So then one would say this is really just a complementary test of our model, right? Okay, very briefly here, the last model I wanted to discuss, a favorite model by the LHC collaborations, so 2x-doublet model, a pseudoscalar, and then a dark matter candidate. I mean, this has been explored in great detail, and we already heard some results about it this morning. You have this scalar particle content, so this is the standard model like scalar, then the typical, in blue, the typical 2x-doublet model at additional scalars, and then you have an additional pseudoscalar and the dark matter candidate and a very long list of parameters. I'm not going to go through. I mean, you have 12 free parameters, basically. Again, the bounds, similar to what I discussed before, what is important now is that you also get bounds from B physics, of course, and like in the IDM, from dark matter constraints, so relic density direct detection, and I did a small pseudo recast from current LHC searches, and these are the codes which I used in addition to the ones I already mentioned in the introduction. So B physics, typical picture again for any 2x-doublet model type 2. Here you have the, okay, still 5 minutes. I can talk slower. Good. So here you have the charged mass, here you have tangents beta, and maybe the colors are not coming out so well here, I don't know. But what is important here is that you basically have a lower bound on tangents beta from BS to mu mu, and also delta MS, but in fact the BS to mu mu is most constraining. This is all allowed, and then this contour here comes from B to XS gamma, and this is something which is relatively new, I mean a year old or so, so there has been an update on this calculation from Nikolai and Matthias, and collaborators saying now that the lower bound for charged mass in the 2x-doublet model type 2 is around 800 GeV. And I think this has important consequences, not only for my investigation, but for anyone who looks at 2x-doublet model type 2, because it will push the lower scale for any of the scalars to a higher value due to interplay with electroweak decision constraints. Then another example for this here are the dark matter constraints. So what you see here is the mediator mass minus 2 times the dark matter mass. So if it's 0, you're on top of the resonance. Yeah. And this is the relic density, and this is the official bound. So you don't want to be above this bound for sure. So you see really this kind of typical behavior here. This is the Higgs, what is sometimes called Higgs funnel, depending on the model you're investigating. You want this to be relatively close. And if you go way too much, at some point, there's no more way that you have enough annihilation not to overclose the universe. So this is important. The color coding here is the dark matter mass. Okay. Good. Then I said, what about E plus and minus colliders? It's already explored infinitely at the LHC, but what about E plus, E minus? And I wanted to also look at a signature which is not realized in the normal 2Higgs doublet model. Yeah. So these are the interesting channels where the A and also the big A can work as a mediator to the dark matter. So you have a missing energy. This is the most promising channel. You get cross sections up to 1 femtobarn, and the dominant final states are TT bar, or TT bar plus ET miss. So the question is then, can I ever be in a parameter point where this second novel signature, TT bar plus E miss, is dominant? So here I plot for all allowed points passing a long list of constraints, the cross sections in femtobarn. This is TT bar at 3 TV. This is TT bar and missing energy, and in fact, and this is the distinction, so to say, so 1. And you see here that in fact you still have some parameter space where really this new signature would be dominant. This is now calculated in a factorized way, so not the full generation of the cross section, but really production times branching ratio. So your real results might differ a bit. And here, this is only via HA. If you include this H, the small a, in addition, but again, this is a number without interference and so on, then you have an even larger parameter space. Okay, thank you. So the bottom line here is that you can find regions where TT bar plus E miss dominates. Okay, and I'm already at my summary and outlook. So the LHC already constrains some models, especially it also does not constrain some other models because they are not investigated, which I think is not so good. And obviously the role of future colliders is equally important. And this picture I stole from Tim, where basically you can see that the BSM Higgs or scalar can connect to many, many important parts in theory and experimental space and techniques.
Thank you. What is nice over your experience in the section? Questions, comments? There's one in the back here.
Yeah, thanks, Tania, for this really nice talk. Could you maybe, since you discussed many models, you addressed in the beginning what the open questions are of the standard model. And of course, many of these multi-Higgs models, they have dark matter candidates, but could you maybe say which of the models can do additional good things that the standard model cannot do, and which are maybe also theoretically well motivated?
Yeah, okay. This is asking for a favorite list, which I'm reluctant to give. So, I mean, obviously, I cannot talk, I cannot look at you. I look at the wall. I look at this guy. Okay. Or I go somewhere else, maybe here. Okay. So okay, so I mean, 2 of the models, as you know, give you a dark matter candidate. Yeah. However, I have to say already in the IDM, it's difficult to really match the predicted relic density. So in a sense, you say I take it as an upper bound, but that's about it. I would say, I mean, my approach is a bit different in a sense, because what I'm trying to do is give some models to experimentalists where at least I as a theorist can say I understand everything. Yeah, so if you start simulating something, I can tell you exactly what you're doing wrong, for example, which is also something you don't know so much. And this two-real singlet extension, for example, really gives rise to new signatures which haven't been there. So we have seen some results earlier for this what I call asymmetric decay, one resonance going to another one and 125. And this is really new now in the experimental agenda, I would say. I know that it would be nice to solve things, right? To explain all the flavor physics anomalies and so on. In our model so far, I started thinking about G-2 in this 2HDM plus A model, because in a sense, you have an additional scalar you can play around with, you have additional parameters, so maybe you have new contributions which go away from, or enhance the possible parameter space. But this, I didn't even start any calculation. So this would be something which could in principle be interesting. Yeah. But for B physics, I think mainly you get constraints. I mean, it's not, so I'm sorry, I cannot tell you this will solve all the questions of the, it's more pragmatic answer. Yeah, sorry.
Questions discussed before by Matthias. You know that another theoretical motivation is the gauge hierarchy problem, and accommodate unless you are considering some symmetry, either supersymmetry, which you don't consider here, or another symmetry would be scaling symmetry, which people have discussed. Myself with Lisa, Alexander, and Unli, we discussed, and other people as we are here, discussed singlet extensions where we have scaling symmetry. Have you explored these models? Because they give also dark matter, neutrino masses, all these beautiful things that are well motivated.
I mean, I would not, I haven't, sorry, but I think probably what could match at least some of these models to some of the extensions we have, and then see at least somehow how the parts of parameter space which are similar.
It's not easy because the potential arises purely radiatively in those scenarios. You have to really work a bit different.
Yeah, but the phenomenology should be similar still, I mean, apart from the dark matter.
You need to translate the theory to phenomenology, you need to do some work. That's what I'm saying.
I haven't done it yet.
Questions or comments? Anything online? One brief question, maybe you doesn't know it. You mentioned Mischek has updated the B2S gamma calculation.
There is a question, in fact, online.
Okay.
Yeah. But maybe your question.
So what's new in this calculation? Do you know by chance?
No.
Okay.
More higher orders. Sorry, but you can have a look. But I think it's important because somehow this has not come through yet to the community, I have the impression. Yeah, I mean, very often people talk about, let's look at Schulz-Doppelt model type 2 with masses of 200 GeV. This is excluded. I'm sorry. Yeah, so one should not press the experimental collaborations to look for something. I mean, then say motivated differently. So I think this has to be emphasized more. Okay.
Is the only question?
Yes, can you hear me?
Yes.
No, just a comment on the last slide. Probably you are including within cosmology, but it would be also good to highlight that, of course, scalars can have a nice phenomenological consequency with phase transitions, and that can be detected gravitational waves. Right. I think that's important to highlight as well.
Yeah. Sorry, it's not okay. You can read it in the cosmology circle. I mean, this is something which has really gained a lot of attention now, especially the complementarity of measuring the couplings at colliders and then relating this to electroweak phase transitions and so on. So there has been a lot of work on this also in the models I discussed. But okay, I didn't present it. So.
Yeah, even beyond. I mean, even beyond electroweak. Symmetry breaking. As Apostolos was mentioning, it can be related to neutrino mass genesis, and then the scale can be also not exactly related to the electroweak symmetry breaking, but to another scale. It can be higher or even lower.
I mean, the advantage of these models is at some point, if you want to sell it to the experiment, you can always map it down to something which it's maybe has fewer parameters and it's maybe easier to quantify in also summary plots, for example, right? I mean, if you have your model with 20 new parameters, it's always not so easy to show.
Yeah. Okay, thank you.
Okay, thank you. Let's thank Tania once more. And we will continue with Marcin Badziak, who will tell us about Flavor-violating Higgs decays and stellar cooling hints in axion models.
Hello. Hello everyone. I apologize for my voice, but hopefully it will survive until the end of the talk. It's maybe too much air conditioning, maybe too much drinking, but whatever. So continuing on questions to Tania, I will present to the tablet model, which in fact solves some other problems than dark matter, but also strong city problem. So, basically, I will connect the two exciting topics of recent years. So, Higgs physics and axion physics. So this is based on my recent work published this paper together with Giovanni Cortona, Mustafa Tawet, and Robert Ziegler. Okay, so it's my outline. So after brief motivation to my work, I will discuss QCD axion and how it can explain so-called stellar cooling hints that I will also discuss briefly. Then I will introduce or review briefly DFS-like models where particularly queen charges of fermions are generation dependent. So it's kind of a generalization of standard axion models. Then I will discuss in the setup Higgs phenomenology, including sizable flavor-violating Higgs decays. And finally, I will show that there is interesting connection between the phenomenology of axion and Higgs. Okay, so very briefly, the main legacy of the LHC so far is that the Higgs has been discovered, the mass has been measured very precisely, and also standard model-like couplings. Well, couplings to third generation fermions are more or less standard model-like, within 10, maybe 20%. But that's important that it's basically only third generation. We just start to probe second generation, but we still a bit far away. Another more disappointing legacy of the LHC is that no BSM particles have been found, but let's be a bit optimistic and think what could you expect from the next rounds of the LHC, including high luminosity LHC in terms of VSM physics. So this is kind of subjective, but to me, like the best progress can be obtained in Higgs physics, precision measurements, and rare Higgs decays, mainly because the high luminosity LHCs will improve the luminosity. It will be order of magnitude improvement in terms of data, while the energy will stay more or less at the same level, so we don't access really new mass scales with the upgrade. So this is the projection of Atlas for the high luminosity LHC for the measurements of the Higgs couplings. So we see that it's really amazing how they plan to measure standard model Higgs couplings. So some couplings can be even measured like at the level of 10%. But what's important here is a new coupling on this list is the coupling to muons, which is expected to be measured with a precision at the level of 7%, which is more or less or even better than some of the couplings to third generation right now. And so this is the place I'm really looking forward to see the result, because maybe it's the place where new physics can jump out. The other thing which is not summarized but is stable are the Higgs flavor-violating Higgs decays, which also will be improved a lot. So, for example, Higgs to tau E and Higgs to tau mu branching ratio will be tested down to 10 to -4. So, and this also will be improvement 1 order of magnitude as compared to the current status. Okay, so it's pretty well known that large deviations in H2 mu and either H2 tau E or H2 tau mu can be obtained in several BSM models, but mostly ad hoc models, like, for example, general to Higgs doublet model, which is a very interesting effective theory for many models. So in this talk, I will discuss studies of rare Higgs decays in a well-motivated framework, which solves strong CP problem via Pechet-Quinn mechanism, which leads to the existence of axions, which is a good dark matter candidate. And on top of that, it's a good candidate, probably the best candidate to explain stellar cooling anomalies observed in several stellar environments. So this will be generalized DFS set type model for the QCD axion, and connection with the Higgs physics is that we assume that the second doublet in this model, because it's kind of the Higgs doublet model, is relatively light. I mean, not far away from the electroweak scale. Okay, so very briefly, so I think many of us agree that QCD axion is one of the best candidates for new physics. So it's predicted by Pechet-Quinn mechanism that solves strong CP problem. It's extremely light particle, sub-EeV in many cases, MEeV or micro MEeV scale, and it constitutes a good dark matter candidate. So this is a slide I borrowed from my collaborator, Robert Ziegler, which nicely summarizes the landscape of axion models. So basically, to have a working axion model that solves strong CP problem, we need some anomalous breaking of Pechet-Quinn symmetry. So we need to have a fermion sector that contributes to QCD anomaly. And also we need spontaneous breaking of PQ symmetry such that axion is a pseudo-Goldstone boson of this symmetry, and this is governed more by the scalar sector. So the QCD anomaly can be obtained either via standard model fermions or some BSM colored fermions. So this divides into main two classes: axion models. So in fact, the one where the standard model fermions are charged under PQ symmetry and contribute to QCD anomaly was the first proposed by Pechet-Quinn, Wilczek, and Weinberg, but it was very quickly excluded, mainly because the scale of the PQ scale was of the order of electroweak scale. So then people focused on so-called invisible axion models, where there's an additional singlet on top of the Higgs sector, and that singlet has a F much above electroweak scale, which allows to decouple axion physics to some extent. So one class is so-called DFSZ models with two Higgs doublet plus a singlet. And when we have QCD anomaly generated by new VSM fermions, then one Higgs is enough plus a single. These are so-called KSVZ models. I will focus on the FSZ models in this talk. So before going to the model, it's helpful to look an axion effective Lagrangian, which describes UV models well below the Pacheco-Quinn scale. So there are basically two important terms in this Lagrangian. So the first one, generated by QCD anomaly, is couples axion to Gruen field strength, and this is crucial for solving a strong CP problem, because this generates the potential for the axion, and also which allows for relaxing theta term to 0, and also generates the axion mass, and the prediction for the axion mass in terms of the axion decay constant is this one here. So it's roughly milli electronvolt scale for Fa equal 10 to 9, which will be a scale that I will more or less consider in this talk, plus minus 1 order of magnitude. The second term comes from electromagnetic anomaly, and it's responsible for axion photon couplings. And this is model dependent part, and allows to search for axions, for example, in helioscopes, which is like very promising place to look for axions because of planned EEST helioscope, which will improve significantly couplings of axions to photons. And the third term here is the derivative coupling of axion to fermions. I just want to emphasize at this point that in general, these couplings would be Flavor-violating. Okay, so very briefly, DFSZ models, as I said before, this is it has standard model fermions charged under PQ symmetry to Higgs doublets, so one more than in the standard model, and the singlet with a VF setting the Pacheco-Quinn breaking scale. So then we can construct to Higgs doublet model Lagrangian consistent with the charge assignments for the standard model fermions. So if the U1 charges and PQ U1 charges are flavor universal, we have only two options. Like there are two models which differ by to which Higgs doublet leptons couple to. So these are so-called DFSZ1, DFSZ2 models with a terminology kind of borrowed from two Higgs doublet type 1 and type 2 models. But just to have like a simple U1 PQ, we need some other coupling of the Higgs doublets to phi. But what's important from my point of view is that in this setup, axion fermion couplings I entirely fixed by tangent beta, the ratio of the waves of the two Higgs doublet, which means that it's not that flexible in terms of playing with fermion couplings, which will be important for the stellar cooling anomaly. Okay, so in fact, stellar cooling anomalies is not a new story. It has been observed in several stellar environments like white dwarfs, red giants, horizontal branch stars of globular clusters. Excessive energy losses compared to standard stellar cooling models. And there is a very nice paper, like 5 years ago now, that was trying to explain those stellar cooling anomalies with several new BSM particles, and it turns out that definitely the best fit among all the candidates is provided by axions, given that they have a sizable coupling to electrons. So eventually, I mean, it's not that easy to. It's not hard to get a axion electron coupling of the right size. but it's a bit more difficult to be consistent with other constraints on these models. And the main killer for many models are the bounds on the neutron axion coupling from supernova 1987A, and also neutron star in cooling. So in typical axion models, these constrain the axion coupling to be above order 10 to 9 GeV, which is also more or less the scale to explain the stellar cooling anomalies. So in principle, like in standard DFSZ models, I mean, it's almost impossible to explain stellar cooling anomalies. Basically, well, this is the DFSZ1 model. I'm not sure if it's that visible, but that studies in this paper, so they made the fit to all the stellar cooling hints, including also constraint from supernova and neutron stars. So the best fit is this red dot. The vertical axis is tan beta. This is horizontal is the mass, or equivalently Fa. So Fa that gives the best fit is roughly 10 to 9. But what maybe is not that visible, tan beta here is like above 100. And in fact, it would be even higher if they wouldn't introduce perturbativity constraint. But this perturbativity is still kind of, we would need to have some new physics curing the perturbativity just above the electroweak scale. So basically, in principle, one can explain this anomaly in the FSZ models, but one need to go to non-perturbative regime, which is very problematic. Okay, so this motivates me to introduce so-called nucleophobic models, where the axion-nucleon coupling is suppressed. So these models were studied by these people here. So basically, yes, so the bounds from supernovae and neutron stars can be relaxed if axion-nucleon coupling is suppressed. And this happens where these two relations for the coupling of axion to up and down quark are satisfied. And this cannot be done in standard axion models. I mean, one of them could be satisfied, but not both simultaneously. But it was shown here that both conditions can be simultaneously realized in generalized DFSZ models, where the PQ charges of standard model fermions are not universal. And this also automatically leads to appearance of flavor-violating axion couplings, which are important for phenomenology. So just to briefly explain the idea, so in this paper they focused on this class of DFSZ type models where the first two generations they still have PQ charges universal, but the PQ charges of the first generation are different. So this is the matrix. If this is the matrix of PQ charges in the favor basis, then when you go to mass basis, you get some of diagonal terms that are governed by the size of the rotations, transforming the base favor basis to mass basis, and this basically is present for each sector, both lepton and quark. So all of this we can parameterize by those rotations, which we call psi, and there are two kind of misalignment angles that are constrained between 0 and 1. When they are 0 or 1, there is no flavor violation, but if at least two psi's are different from 0, we have flavor violation. So I cannot go much into detail with the models, but just to say that there are 4 charge assignments leading to nucleophobic models, depending whether Q or U, this sector is universal. So basically, different models depend on how given quark bilinears couple to Higgs double, whether to one double to the other one. And also there is a similar story in the charged lepton sector, where we also have 4 options. So in total, there are 16 nucleophobic models. The couplings are summarized in those tables. Well, I don't have much time to go through all of it, but basically, so this E over N is the electromagnetic anomaly coefficient from quark sector and lepton sector. So we should take the sum when evaluating, for example, the axion photon coupling, and then the resulting prospects for Yaxo and so on. So let's now go to axion phenomenology, just discussing some benchmark models. So first of all, we neglect quark flavor violation. So this can be done by setting only one non-zero psi in the quark sector. This in principle could be present. In fact, it leads to interesting quark phenomenology, well, quark axion phenomenology, but from the point of view of the stellar cooling anomalies, it does not affect much the overall picture. So for simplicity, we neglect this. And then nucleophobia sets the value for tan beta. So tan beta should be roughly around 0.7. Of course, we don't need a precise cancellation of the nucleon coupling. So, but one should remember that tan beta should be close to this value. One should also set psi2 in the lepton sector close to 0. Otherwise, mu2e gamma and mu2e axion decays would kill the model. So eventually, axion phenomenology is determined by one parameter, psi11, which controls coupling to electrons and flavor violation, and tan beta. So these are the prediction for axion phenomenology for 2 of those models. Okay, so between the blue curves, it should be filled with blue. So, but somehow it doesn't show up. But yes, it should be here. Yes, so the part of parameters with that explained cooling region is this one between the blue curves. For 10 to 9, for 10 to 8, it's here. What's important at this point is that in contrast to standard EFSZ models, cooling hints can be explained for large range of tan beta, so there is no problems with perturbativity, and also large range of psi1. Moreover, if we go to FA of order 10 to 8, thank you, then the cooling hint consistent with supernova bounds is this small region of tan beta. So we see that psi11 has to be necessarily different from 0 or 1. So basically bounce from supernova enforce some flavor violation, and it will lead to Higgs, Higgs physics. Okay, I have only 2 minutes, and I'm okay. So maybe I will go now to Higgs decays. So just very quickly. So the point is that if we want to explain stellar cooling hints, we need to introduce flavor-violating couplings, axion couplings, And if this happens, we have also flavor-violating Higgs decays, provided that the second Higgs doublet is relatively light. So we parameterize the effects of the second Higgs doublet as often done into Higgs doublet model by cos beta minus alpha, which is set more or less by the scale of the second Higgs doublet mass. Okay, so there are different models, different charge assignments, which give to different constraints from LHC, because basically to maximize the effects of Higgs flavor-violating decays, we need to maximize cos beta minus alpha, but this is also constrained by the standard LHC Higgs measurements. So this plot shows basically, so the region between blue curves is allowed by the LHC Higgs sculpting measurements, while this orange region, it is the region that is constrained by Higgs to tau E decays. So current constraint is 0.22%. So just to summarize those plots, the main point is that basically we can have in those models Higgs to tau E decays branching ratio as large as allowed by the LHC. So in a sense, we can see new physics here anytime. And there are also, okay, I am going to finish soon. So Higgs decays to muons are also modified. And basically, these are the final plot. Maybe I will go to the case of Fa equal 10 to 8. So what's important here is that we should look basically more or less in this region, because this is region consistent with supernova bounds and neutron star constraints. So we need tan beta close to 0.7, as I said. And in this region, it's hardly visible, but we can have Higgs to tau E decays of more than 0.1%. So even though the parameter space is so shrink, the Higgs can be still sizable. And also we can have Higgs to mu like 60% above the standard model prediction, which is in fact something that could be even seen in the next run of the LHC. So just to summarize, in non-universal DF-set models, easy to accommodate scalar cooling anomalies. And I haven't said much about YAXO, but what's take-out message here is that the cooling hint region can be probed by YAXO helioscopes and at the same by the Higgs searches at the helium LHC. Thank you, and sorry for going over.
For this interesting talk. We still have time for one or two questions. Yes, Krzysztof.
In your models, you have a flavor change and neutral currents, right? Do you have any mechanism to suppress these currents, because they are very dangerous, as you know?
Yes. So this is from this point of view. So we just parameterize this by those size. So in this work, so basically up to the fact that we need to recover CKM matrix, these are 3 parameters. But in fact, the original motivation behind the neutrophobic models was the connection between the Fermi mass generation and the PQ symmetry. So basically, in models where PQ symmetry is associated with, or is a subgroup with a horizontal group that sets the scale for the Fermi masses, then in fact these are those sizes are really predicted. So, and this
Are they predicted to be small, the couplings, or
just fit? Yes. So they well, there's still some you still fit. I mean, of course, the horizontal symmetry sets you additional constraints, but still there's some freedom, right? But I mean, that was not my work. It was more by Robert Ziegler about this flavor axions. but that's really very interesting idea, and I don't know exactly how much freedom you have. So I mean, it was not really my work, but in principle, it's not. I mean, those size can be constrained from modality point of view, and apart from the effects in standard flavor physics, there are no search channels for actions in B factories and so on.
There's one more question by Philip.
Question from experimentalist. You refer to this cooling anomalies for supernova and neutron star. Okay, I don't know this result. Maybe you could say a few words more, but because my feeling is that there are still quite a lot of uncertainties in this estimates, mainly based on some nuclear processes, which can be clearly accommodated without our standard knowledge, without any need. How need for BSM? So how firm are these anomalies, how we call it?
Mm-hmm. So, I mean, I would say your statement is true for any claim from astrophysics, right? But so this is somehow, I wouldn't say, even if they claim like 4 sigma, it's not the same 4 sigma as would be for the Higgs, right? So this is like, so when I say there are some excessive energy losses, this is on top of standard stellar evolution models. So of course, those stellar evolution models, they, to some extent, they are phenomenological models, but in a sense, this is the best what astrophysics can provide us. So given that there are several places where it does not fit those standard models, it's a hint, right? I mean, but I agree that maybe the systematic uncertainty are just not under control enough. So, and I mean, to be honest, I mean, it's probably the most likely answer, but given that there is no much hint, I would say those hints are one of the most interesting ones.
Thank you. Thank the speaker again. We come to our next talk by Krzysztof Meissner, who will talk on E10 symmetry, dark matter, cosmic rays, and giant black holes.
Thank the organizers for the invitation. So show the screen. Yes, that's the idea. Let me see. You are seeing me as an organizer. Share screen, yes. Okay, and okay. Okay, again, sorry. There are some reviews. Okay. Here it is. Okay, thank you. My talk was about the new symmetry, in a sense, incorporating gravity into the particle physics. That's E10 symmetry. But since the meeting is devoted to the standard model and beyond, I will start from the conformal standard model that we proposed with Hermann Nicolai 14 years ago, before the LHC started. I would like to emphasize. So we assume that there is no low energy supersymmetry, that the low energy supersymmetry is replaced by conformal symmetry, and that's the model that I would like to say a few words about. So we assume that there are no new scales below Planck mass. There is a grand desert beyond the weak scale. The cutoff is a bona fide physical scale. So we don't hide the problem of the quadratic divergences within the dimensional regularization, because it's only hiding the problem and not really solving the problem. The model should be viable up to lambda. The vacuum should be stable. We know that in the standard model it isn't. There are no Landau poles up to the Planck scale. That the model is defined at lambda, at the Planck scale, and it is renormalizable there, and require vanishing of quadratic divergences. That gives us two more constraints it is important. And the seesaw mechanism for neutrinos. So we have right chiral neutrinos, of course, and B minus L is broken spontaneously by but explicitly only by gravity. And that's another requirement, that it explains the observed baryon to photon ratio. We know that the standard model with its CP breaking is not explaining the baryon to photon ratio. This number would be 10 to the minus 14 for the standard model, and we know that it is 10 to the minus 10 because we have a new source of CP breaking. So the model itself, I just flash it to show that it has only a few more parameters. The yellow ones are new ones with respect to the standard model. The white ones is just the standard model. We introduce a new complex field that couples to Majorana coupling to the right chiral neutrinos. And the last term is assumed gravitational breaking of order 1 over Planck mass squared. It has only a few more parameters on top of the standard model. So the standard model has only weak scale neutrinos, these right chiral mostly neutrinos, complex new scalar phi. The real part of phi couples to phi through the mixing. So the actually 125 GeV, what was measured at LHC in this model, is a mixture of mostly doublet and a little bit of this new one. There should be another orthogonal combination that would be mostly new one and a little bit of the doublet. And that's the way both are mixtures. So, and we can predict, in a sense, when the mixing angle is given, we can predict the mass. We don't have a mass of the new one, but we are waiting for the new Higgs-like particle, but very narrow, because the mixture of doublet is very small. So the phase of phi couples to standard model only through the Y nu, the Yukawa coupling, and mass is from assumed gravitational breaking. So it is axion-like particle. So there is broad-angular Higgs mechanism for electroweak symmetry breaking and spontaneous symmetry breaking for lepton number symmetry, because this new field has charge number, has lepton charge -2, because it couples in a Majorana-like way to right chiral neutrinos. So it couples spontaneously lepton number. And of course, the seesaw mechanism for neutrinos. We assume that the scale is of the order of the weak scale, but the coupling is very small. This Y nu is very small. So we have masses of neutrinos from the seesaw. So it is not a large scale and coupling of order 1 that is usually assumed for the seesaw mechanism. We have coupling, the Dirac coupling is of order 1, the YM is of order 1, but the coupling to right chiral neutrinos is very small. So that makes the mass small. And that assumption, Y nu is very small, makes all the precision tests of LEP viable because the new sector doesn't couple to the standard model or couples very, very weak. Okay, so SM is unchanged in the usual sectors. That's what I already said. Only a couple of new parameters. I recall that minimal standard model had 115 new parameters. It turns out that the vacuum is stable. We checked that there is no going underwater about 10 to the 10 GeV, usually for the standard model. It goes up to the Planck scale above 0, the self-coupling. All couplings can be small. If we start them small, they do not run. A set of new particles is the right chiral neutrinos. We always have them with the seesaw mechanism. They are very weakly coupled to the standard model. One scalar around 1 TeV, but mass depends on the mixing with the doublet. So mixing with the usual Higgs. So phase of new scalar field is very light and extremely weakly coupled. So it's an axion-like particle. Hierarchy problems. And now I come to these two additional equations that we impose. So in essence, they are not seen in dimensional regularization. As I said, it hides the problem of quadratic divergence because we then have to go to 2 dimensions to see them. But in 4 dimensions, we see only logarithmic divergences by the dimensional regularization. So when we calculated treating lambda as a bona fide bare physical scale, so we impose the coefficient in front of the, because the only 2 parameters that break, that are a problem in the standard model, there is 1 parameter, m squared doubled, Higgs doublet squared. That's the only parameter that breaks conformal symmetry that has quadratic divergences. Now we have 2 scalars, so we have 2 such parameters. So we calculate the coefficient in front of m squared, or in front of the quadratic divergence, and we impose them to be equal to 0 at the Planck scale. But it turns out gravitational corrections turn out to be small. That was shown in this paper before. But it turns out that once we impose them at the Planck scale, they are valid all along. So once we impose that there are no quadratic divergences at 1 scale, there are no quadratic divergences at any scale. So they run in a sense together. Okay, so when we impose these conditions and we add the baryon to photon ratio that we want to explain 10 to the minus 10, then we have a set of 3 equations and we have 4 new scalar couplings. So in a sense, it's almost fixed. If the new Higgs, the partner of the Higgs, was discovered, so we knew the mass and the mixing angle, then all 4 of them, all 4 new couplings would be fixed uniquely, and then the model could be falsified fully. There are other discovery of the new Higgs like scalar will make it unique. It does not concern the CP, the new CP phases that are in the Majorana coupling of right chiral neutrinos. They are very important. So now they are, for example, important for Higgs into tau tau. So these new phases could be there as new CP breaking. And we know that we need the CP breaking, another source of CP breaking, because we cannot explain matter-antimatter asymmetry in the universe. So anyway, there should be somewhere the new source of CP breaking. So the anomaly, which is the trace of the T mu nu in a quantum sense, of course, is given by this expression, where C squared is the Weil squared and T4 is the Gauss-Bonnet term. Now, there are some theoretical uncertainties depending on the off-shell extension. I will not stop on that. The non-uniqueness can be of this result can be fixed by the Vez-Zumino consistency condition. So we are left only with 2 terms, C squared and Gauss-Bonnet, where the coefficients, every field gives a contribution to CS and to AS. And actually, it was very difficult to find these coefficients for gravitino and graviton. 0, 1, half 1 are known for 30 or 40 years. But the contributions from gravity and from gravitino were difficult to find. We find them in one of the Zeitlin papers after 2 weeks of recalculating. So there remains a non-uniqueness, namely the scalars can be replaced by antisymmetric tensor in 4 dimensions. We are all talking about 4 dimensions. It changes A0. So those are the numbers. As you see, they are very strange, for example, for 3/2 and 2. And that's what we have obtained in this paper, these 3/2 and 2, the rest was known. But our requirement is that the anomaly should vanish. Therefore, we should find natural numbers, ns, n0, n1/2, n1, n3/2, and n2, so that the sum of the left column is 0 and the sum of the right column is 0. With these strange coefficients, it seems that some very large natural numbers should be needed to cancel them. But actually, to our great surprise, it turned out that the field content of supergravities, not 1, 2, 3, 4, they do not satisfy these conditions, but 5, 6, 7, and 8. 7 and 8 is the same supergravity. So let's say 5, 6, and 8, with these very small numbers, satisfy these conditions. So that was very, very surprising. That is probably connected to the fact that they have an absolutely incredible finiteness properties, as proven by the maximally helicity violating amplitudes, up to 4 loops and starting on. Only those, but the first 4 do not have these properties. So this only n equals 8 supergravity of those has enough fermions to contain 48 degrees of freedom of the standard model. I'm talking about fermion degrees of freedom. So we have 6 quarks, each of 3 colors, and we have 6 leptons. Each one has 2 degrees of freedom, so we have 48 degrees of freedom, fermion degrees of freedom in the standard model. So only n equals 8 supergravity, because it has 70 scalars. It will be important on the next slide that it is 70 scalars, 56 fermions, which is more than 48, 28 vectors, 8 gravitinos, and 1 graviton. That's the content of supergravity, but we do not claim that n equals 8 supergravity is anywhere realized as supergravity. So interactions are not supergravitational. We take only the field content, because the symmetry will be replaced by something much bigger, much infinitely bigger than n equals 8 supergravity. I will discuss this in a minute. So these numbers are important, 70, 56, and 8. If we break supersymmetry fully, that means that 8 fermions would go as a massive, as a third component of gravitino. We are left with 48 degrees of freedom. And that is what Gell-Mann noticed. Morais-Gell-Mann recently passed away. Okay, so E10 symmetry. It was noticed by Kremer and Gilliard at the end of the 70s that n equals 8 supergravity, that can be understood as a compactification of 11-dimensional n equals 1 supergravity to 4 dimensions, exhibits global E7 symmetry. Normally, one would expect SU8. We have 8 charges that we can rotate any way we like, but it's bigger. It's E7. And actually, they noticed that if the local SU2, which has 63 adjoint representation, when we add 70 scalars, we have 133, and it's the adjoint representation of E7. And they actually realized this E7 as a global symmetry on n equals 8 supergravity. So that was a huge surprise that the symmetry is much bigger than just follows from naive rotation of supergravity charges. Okay, so going further, if we go down to d equal 1, so that's from 11 to 4, we have E7. So we expect going from 11 to 1, when we have only time component, it should be E10. So, and what is the reasoning? In the early universe, the time coordinate was the most important one, because no one knew its neighbors. Yes, because when we are at the beginning on the Penrose diagram, we go up, in a sense, vertically up. So in a sense, we don't know we cannot build a field at the beginning, spatial part of the field. So that's the idea. So we expect E10. Then we can write a Dynkin diagram for E10. Since we know we have the classification of compact Lieb groups, and E8 is the biggest one, that is a different thing. The full representation of such involutory or maximal compact subalgebras, it is hyperbolic, is unknown. Mathematics of this is largely unknown of these. For n bigger than 8, they do not belong to any standard class. For smaller n, we know that, for example, this involutory k of A7 is SU8 and k of E8 is spin 16 over C2. But we have E10. So n equals 8 supergravity, as I again flashed the field content. That points to an infinite symmetry group E10, and it's really infinite. Infinite and infinite can be different. This is really horrendously infinite group. Of course, the number of generators is infinite. It exponentially grows with the level, and that's a horrendous thing in a sense mathematically. But it unifies gravity with all the other interactions in a very different way from any GATT or string scenario. I spent 17 years on string theory. So I really can say that it's very, very different. So, but since the mathematics is largely unknown, we have to dig out some information from this E10. And one observation is that after breaking all supersymmetries, we don't assume any supersymmetry below the Planck scale. The theory is completely non-supersymmetric. It has exactly 48 degrees massless degrees of freedom, fermion degrees of freedom, as in the standard model with 6 quarks. So Morais-Gell-Mann noticed that, and that can be an explanation of 3 generations. There cannot be more, and there cannot be less than 3 generations, 6 quarks and 6 leptons. Morais-Gell-Mann had a problem with assigning the charges, because quarks and leptons, they are okay, that they are 3 triplets and so on. But and electromagnetic charges turned out to be different by 1/6. For example, electron has -5/6, neutrino has 1/6, and so on. So that was a problem that Gell-Mann noticed. And when the symmetry is broken, that's what Gell-Mann did, it requires a very natural deformation of the coproduct, and all 1/6 go into place. So electron has charge -1, neutrino has 0, up quark has +2/3, down quark has -1/3. Everything fits into place with a very natural deformation of the coproduct. So it is not part of the gauge symmetry. It belongs to E10 and not to gauge symmetry SU8. Okay. SU2 plays a very different role than SU3 color times U1 electromagnetic. So normally we expect that when we go up above 100 GeV, SU2 will be more and more visible, will be more and more exact. While at the low level, in this room, for example, we see quote unquote SU3 color. Of course, there are condensates, of course, so we don't see that exactly, and U1 electromagnetic. SU2 is not realized at low energy. In this picture, SU2 is never realized exactly. It's an approximate symmetry up to the Planck scale. So, and K of E10, that's a very important thing, predicts the existence of very heavy, fractionally charged, electromagnetically stable and strongly interacting gravitinos. So, and now I come to gravitinos, because they are Planck mass, so one would say there is no chance of seeing them, but actually there is, and that's what I want to talk about. The 8 massive gravitinos are charged and split under SU3 color. We have a triplet, anti-triplet, and 2 scalars, and 1/3 is the electromagnetic charge. So they are subject to strong interactions, so in a sense they can combine with for example, D bar, making a quote-unquote meson out of it. Okay, so, but there is a fractional electrical charge. They would be stable. There is nothing that they can decay to such objects, even to quarks or whatever. The electromagnetic charges do not fit. Therefore, that was a problem, because if they are stable, they should be around us. But around us, they would be dark matter. Dark matter shouldn't be charged. So what's the problem with this? So that was, they should be around us. So the question is,
why they can be dark matter or they cannot. And it turns out that electrically charged dark matter are of course very strongly constrained by the data. Dark matter comes from the fact that this matter does not interact with photons, so it shouldn't be charged. But when you actually look at the observational bounds on the charge of dark matter as a function of its mass, that's a rough estimate, roughly. So when you have the usually discussed dark matter candidates that are 1 TeV around, when you plug to this formula, you see that the charge can be extremely small. That's the name, the dark matter. That's where the name dark matter comes from. But when you plug in the Planck mass to this formula, you get something of order 1. So the Planck mass dark matter is not constrained to have very small charge. Why? Because we know the density of dark matter in our universe. When we divide by very large mass of dark matter particles, there are very few of them. Actually, 1 in a cube, 20 by 20 by 20 kilometers, roughly, on average. So that's why they are not constrained. Therefore, our 1/3 or 2/3 fit into this formula. So they can be dark matter if they are extremely heavy. So that's our prediction, that these gravitini are dark matter. So actually this neutral, not strongly interactive. But they are charged and very heavy. So if they have for example, they could be very easy to see in any kind of detector because they are very slow. Presumably they have the velocity of the Earth around the sun or something, 30 kilometers per second, but they will be ionizing all along. Muons have to be very fast to ionize like them. But sorry? They can be mesons. For example, they can be with D bar, for example, to form a meson. But we are talking now about the gravitinos that are neutral with respect to color, these 2 ones, not these 6 ones. Yeah. Question for yeah. They are neutral ones. Yeah. Okay. So they should be very easy to see, except that they are extremely rare. So it is very rare to see such an object, which is, but they would go through the Earth, ionizing everything and not stopping because the energy is extremely huge. So what are the other? The gravitinos should gather in stars, presumably. But when we calculate the annihilation rate, the only way to produce something is by annihilation. When the annihilation rate is too small in the sun, for example, so we will not see anything. So, but we propose that if the star, not our sun, if the star collapses to a neutron star, the annihilation is big enough to see the products. But the products should be produced in the skin of the neutron star, because otherwise that would be absorbed by the neutron star. So in the skin, there are mostly iron nuclei of the neutron star. So our prediction is that they should be light nuclei coming out of the neutron star. And they should be the ultra high energy cosmic rays, the biggest energy cosmic rays, should not be protons, but should be light nuclei. And actually, this is what Pierre Roget Observatory measures. For the largest energies, there are not protons, they are light nuclei up to iron, which is very surprising because normally we would say that protons should be accelerated, like in a Fermi shock wave or whatever. That is our prediction, that they should be light nuclei. We have calculated the flux. It roughly is of the order observed rate, 1 event per month and per 3,000 kilometers squared. Another observation, if there are observation of black holes very early in the universe, before 1 billion years, that have more than 1 billion solar masses. And there is not enough time for the usual evolution that we have a star dies out, it collapses, there is a black hole, and black hole accretes everything around. There is not enough time because the first stars were at more than 100 million years after the presumed Big Bang, which was not there, by the way, I guess. So there are billions, 1 billion solar masses, they are observed, and there are no known mechanism of producing such monstrous black holes in such a short time. But gravitinos, as we have shown, can provide seeds even in the radiation era, very deep, very early on, can provide seeds of such black holes in the radiation era. We have solved the Einstein equations to show how they grow and so on. And they will eventually coalesce before collapsing into small black holes. It turns out that the effective masses of such a black hole created by this mechanism, so there are seeds growing by the expansion of the universe, is at the interval 10 to the 5 solar masses up to 2 billion solar masses. So there should be a gap of the usual solar masses and the solar masses created by this mechanism. So let's go to the summary. Conformal standard model has definite unique predictions for LHC. Beside the Higgs particle, one Higgs-like very narrow heavier scalar. If it is discovered, we can fix all the couplings and we can see whether it fits what we predict. Right chiral neutrinos are too weakly coupled to be visible. The prediction is almost unique. Full uniqueness would come with the discovery of a new Higgs-like scalar. That's why I'm very much waiting for what LHC will see after starting in March. This infinite group going bottom up, well, on top bottom, infinite group is broken at the Planck scale and it provides a completely novel unification of all forces. One of the predictions is that 6 and only 6 quarks. If LHC sees any fermion of spin 1/2, the whole thing is over. The whole thing is gone. It predicts only those fermions that we see, that we have seen as the only fermions of spin 1/2. There are also 8 fractionally charged, stable, strongly and electromagnetic interacting Planck mass gravitinos. Being extremely massive and therefore very diluted, they can be candidates for dark matter even though they are charged. Their annihilation in neutron stars can explain the origin of ultra-high energy cosmic rays, in fact nuclei observed on Earth. And their clumping in the very early universe can also explain the origin of observed giant black holes. Time will tell. Thank you.
For this interesting talk, we have time for questions. Yes, of
Okay, first of all, just to comment, the first perturbative scale invariant. There are 2 ways to get conformal standard model. One is to gauge the U1. I think your model has an extra U1, global U1. And to gauge this U1, this is what's done by Ralph Heffling together with this singlet field. And the other is your scenario where you don't have you don't gauge the extra U1.
No.
But you have a global U1. And then, of course, there were a lot of calculations at that time after your work with Folkas and Foot and myself. And we found that there is a Ladau pole in 510 TeV range. So the only way, okay, that means the theory won't become perturbative in the Planck scale as announced. The only way to do it, you have to abandon this U1. I don't know whether this improvement has taken into account in your calculations in this new setup, or you just considering this old constructions?
Yes, that's also involves papers that were much later than 2007. 2007 was the first proposal in a sense, but later we have slightly modified we can talk about that in private. Yeah.
If you have U1, there are plenty of papers and they are saying that
we don't have U1, the gauging of gauged U1.
The lifting of U1 was our paper.
Okay.
Our paper.
Yeah. Okay. Yeah.
And make the model perturbative to the Planck scale.
We didn't have gauged U1. Yeah.
Alexander actually.
Yeah.
Okay.
Right.
Maybe you can continue this. There has been a question here, and then Matthias.
Yeah. Fully agree.
What is the production mechanism to get the correct abundance for dark matter?
That is the question that we cannot answer. Namely, for us, the dark matter are those that are not strongly interacting, only those 2 that are not strongly interacting but charged. For strongly interacting, we can calculate the abundance because it is in thermal equilibrium for some time before it decouples. The others, when you calculate the annihilation rate, which is extremely small, they are never in thermal equilibrium. So in a sense, they inherit the abundance from the previous era that we cannot calculate. So the others, the strongly interacting, the abundance is so small that they cannot be dark matter. But the non-strongly interacting, the gamma is never bigger than H in a sense. So they inherit, so we cannot calculate the abundance of dark matter because they are never in thermal equilibrium.
Okay. And the last question by Matthias.
This goes back to the beginning of your talk, basically, where you mentioned the cancellation of quadratic divergences. So, of course, this is an old story, but I mean, in the framework of your model, what is the dynamics that enforces these relations? I mean, how do the gauge couplings know that they have to satisfy these linear equations? I mean, if there's a very small departure from these equations, you get back to quadratic divergence, right? So they really have to be imposed exactly, but what is the mechanism that
that's what we call soft breaking of conformal invariance. In the same way as you do not allow in supersymmetry to make hard breaking of supersymmetry, so that the number of degrees of freedom, fermionic and bosonic, they should always match that the soft breaking. We assume soft breaking of the, because that changes the symmetry of the system in a sense. If you don't have, from that point of view, all masses that you have are very, very small with respect to Planck scale. The theory is almost conformally invariant. So in the same way, and it's in supersymmetry, when you break it in a soft way, you cancel the contributions to the quadratic divergences among others, yes, because the positive and negative contributions cancel, but you never are allowed to add something that explicitly breaks the number of degrees of freedom. So in the same sense, we called it soft breaking of conformal invariance, in the same way as there is a soft breaking of supersymmetry that will never change the degrees of freedom, fermionic and bosonic. Absolutely. Yes. Yes. Exactly. Absolutely. Yes. Yes. Yeah, that if you use different thing in supersymmetry, you would break it in a sense. Yes.
I have a different question.
Yeah. Okay. Maybe a very last question because time is pressing, and then I propose to have the other discussions during lunch. So please, the very last question.
I wanted to ask if you have a prediction for the proton lifetime.
We looked into it, but because this new sector is extremely weakly coupled to the standard model, probably the present constraints, I cannot answer this, but the rough calculation shows that the proton lifetime will not be surpassing this 10 to the minus whatever 30, 10 to the 35 years or whatever. It will not be below that because of this extremely weak coupling of the new sector to the standard model by this Y nu, by this Yukawa coupling of the new scalar through the right chiral neutrinos and from the right chiral neutrinos to the sector, to the observable sector. So it will not change the proton lifetime. Because B minus L, for example, if B minus L is broken only by gravitational interactions here, no, I would say that the proton lifetime, that it doesn't provide any mechanism to making the proton lifetime smaller.
Okay, thank you.
Okay, thank you. Let's thank the speaker and all speakers of the session. The lunch break is as usual until 4 o'clock.